Well, I'm pleased to open this morning's session giving you a talk on and a survey about flow measurement in open channels by using ultrasonic phased array sensors. So, well, our emphasis is on open channels rather than on filled tubes. Ultrasonic measurement is state of the art. The systems which are in operation consist of a receive transmitter which sends a pencil beam into the water and collects reflections from particles. As the beam is tilted with respect to the flow direction, the turnaround time of the echoes changes, resulting in a Doppler shift or resulting in a changing time, which can be evaluated to calculate the velocity of the water. Our proposal is now to apply a phased array for the flow measurement, because the natural shortcoming of the pencil beam solution, which is state of the art now, is that it doesn't collect enough information across the cross section of the open channel. We propose also an array which is swimming on the surface to avoid coverage with sludge, which is inevitable as time goes by. The advantage of a phased array is that it is able to send different beams on a fan into the water and therefore collect more information about the velocity. It covers a considerable part of the cross-section of the channel, not the whole cross-section. Natural shortcoming is that at angles beyond plus minus 60 degrees, the phased array degrades. The phased array is also able to adapt to changing cross sections, which may be possible if the water level changes or if to the walls there is sedimentation. For high performance solutions, we propose a dual array sensor which covers almost 100% of the cross section. Now, phased array technology enables by phase shift from element to element to direct beams in any direction within the coverage of plus minus 60 degrees. At a very early point in time of our project, the frequency was defined to be 1 megahertz for different reasons. And this means that the wavelength is about 1.5 millimeters, and we have to deal with an element spacing not more than 1/2 of wavelengths of 0.75 millimeters. In the lower part of the picture, you see the principal outline of our array, which consists of a piezoceramic structure, an impedance matching layer on the water side, and also some coating in order to avoid impact of water. Well, we had to learn that it is quite a tough thing to handle the piezoceramic material, which is lead titanate zirconate. We at the end ended up with milling the phased array with grinding. The picture in the left side shows the grinding wheel with a thickness of 0.1 millimeter, and we made a lot of experiment with respect to hand of rotation, rotation speed and speed of the feed in order to minimize the waste of grinding wheel. On the right side you see then the ready array. And here you have a microscopic view of the structure in the piezoceramic material. This shows the array with packaging. We created a standard interface for all our samples. As you see here in the middle is the array, and the PCB behind that is dedicated to excite, to drive the single array elements. All is covered by a tube. The receiver and transmitter is outside of the water and is connected through a cable with a waterproof connection to our antenna. This is one sample of the antenna pattern which we achieve. Well, a radar engineer might not feel comfortable with such a pattern because it's not perfect. But we have to bear in mind from a systems and operational point of view that our task is not that of a radar engineer. A radar engineer has to guarantee a high probability of intercept and a low false alarm rate for any target, think on military applications. This is not our task. Our task is to collect enough information on speed of particles within the channel. Next picture shows our test bench. This is owned by Nibus company in Germany. It is a some 100 people company which is a market leader. It shows here a channel 45 by 45 centimeters. It's driven by a calibrated pump, so we know exactly the throughput, the flow. You see here the flow direction indicated, and here you see our device. The white thing is the tube around the array. This is the front of the array, and here you see the cabling to the receive transmitter outside of the water. Well, the next picture shows the basic geometric outline of the channel on the upper left side, and on the upper right side a flow model, which was published among others by Soyek and Teufel, which is suitable to calculate the throughput in a channel. On the picture below, you see measurement data which result from tracking particles, and the model of the flow adapted to these particles. If you look in the 3D picture from the back side, you see that all the measurements are aligned in the principal directions of the beam. And the question now is, which is the angular resolution which is required, and which is the field of view which is required for sufficient calculation of the flow throughput. Well, we made a lot of parallel to experiment, a lot of simulations. This shows a Monte Carlo simulation where the angular resolution on the x-axis is shown versus the relative flow error, which results then from integrating over the velocity in the open channel. This is a simulation for a field of view of plus minus 90 degrees, so we see almost everything. We have 40 particles, 40 echoes which we collect, and we calculate then the flow, and you see that the field of view, the angular resolution is not the main design driver, because the error resulting is in the order of some 1%. More important is the field of view which is required for this sensor, and you see here the field of view should be in the order of 40 to 60 degrees, which we achieved with our array. And another thing which is important is the number of particles which you connect prior to adapting the flow model to the tracked data. You see that the error decreases considerably if you have enough particles, let me say 40 to 60 particles over the cross-section. The angular resolution in this picture is 10 degrees, as you've seen before. Well, again, the model on the upper side, you see we have to adapt the model to our measurement data by adapting A, B, C, and D of this model. This is a problem of a minimum mean square error calculation. The matrix notation is seen in the middle part of this. We have n measurements, and we could solve the least square problem by calculating the pseudo-inverse as shown in the last row. This is a solution which works with MATLAB and works with the PC, but not with an embedded system. It would be a crazy task to make a 40 by 40 matrix inversion. So this doesn't work. So we decided to implement the whole algorithm by means of a QR decomposition using householder transformation. This transforms your D matrix into an upper triangular matrix and a zero matrix below. So you can calculate the Euclidean norm of your remaining error quite easily, and you end up with an expression here. One term doesn't depend on x, which is the vector of our. Sorry, something appears here. I don't want to. Okay, well, the second term doesn't depend on x, is not so important. The first term, as you see, depends on x here, and the minimum solution is that this term becomes zero. And this can be calculated easily, as you see above, due to the triangular shape of the matrix. So you can, by back substitution, calculate the parameters and then apply the model to your track velocities. Well, let me come to the end. The conclusion is open channels do not have a constant, flat, but a curved velocity profile, and therefore velocity data have to be collected over the whole cross-section or a considerable part of the cross-section to calculate the flow with the required estimation precision. An obvious solution to this problem is a phased array, because it can direct beams on a fan into the water. We have discussed the operational needs for the equipment, and there is no need really for a high angular resolution, which means we can operate with a small phase array, only a couple of elements. We choose 8 elements. So we can meet the requirements of the market for a low-price equipment. What is of importance is the field of view. It should be, as we have seen, at least 60 or 40 to 60 degree. A lot of velocity data we have also seen are required to be processed simultaneously. Algorithms exist that allow such an implementation on a smaller microcomputer. We have implemented it on an ARM7 processor and have shown that with all the rest of the single processing algorithms, we can achieve an update rate of 1 to 4 seconds, which is adequate for such a sensor. The lower part, the picture shows the inflow channel of Ulm's wastewater treatment plant, and we have demonstrated here in this channel 1.5 by 1.5 meter that our algorithms and our sensor operates quite well. Well, although Manuel, Haide and me are dedicated as authors or nominated as authors of this paper, I would like to outline at the end of my presentation that a great team, as shown here, made contributions to this work. Thank you for your attention.